Right, so we were discussing the true linear relationship between x and y is this. It's using our population parameters of beta plus some random error. And we're going to estimate it using yi hat, which is our predicted value of y, from our estimated coefficients. So our b naught is our intercept plus b1 is our slope times our data x. So this is what we're trying to do. That's the goal of this chapter. So the goal, we now need to decide what line is best, right? We can make an infinite number of lines, which one is best. So we need to discuss the difference in our response value and our predicted values. So we want to look at the difference between y's and y hats. So this will be called a residual. So residual. And we'll just refer to it as EI, which is equal to YI minus YI hat. So residual. It's basically telling us how inaccurate are our predicted values. So residual. EI, the difference between the actual value of y, the response value, and the predicted response value, y hat. So how do we decide on b naught and b1? So what we want to do is we want to minimize the squared residuals, or the sum of squared residuals. So that means what we're doing is we want to choose b1 and b naught and b1 to minimize the sum of our squared residuals. So ei squared, I equals 1 to n. We want to minimize this. So let me just write out the equation. So that would be summing the squared residuals. So sum our actual values of y minus our predicted values of y from I equals 1 to n. So this is our minimization problem, right? We're trying to minimize this. So where does that happen? Well, for b1, our slope coefficient, it will be equal to the covariance divided by the variance of x. So let me write this out. So this is going to be the sum I equals 1 to n, xi minus x bar times yi minus y bar divided by the sum I equal 1 to n, xi minus x bar squared. So we're going to call this a number of things. We might call this as the sum of squares between x and y over the sum of squares of x. But what you will be more familiar with will be the covariance between x and y. So the covariance between x and y divided by the variance in x. This is how we calculate our slope. So we can think our numerator, okay, how do x and y move together? Divided by the variation or the variance in x in the numerator. So again, when we think about our rise over run, right, rise over run, well now our rise is, okay, how do these things move together divided by, okay, how does the x variable, the run variable, what is its dispersion variance look like? So that is how we estimate b1. But b naught, the intercept, so this will just be equal to y bar minus b1 x bar. So that's where x bar and y bar are the sample means of x and y. Okay, so I know I repeat myself a lot, but again, we are trying to estimate this. We are trying to estimate this equation, the true regression line. We're going to do that using our estimated regression line. So we will estimate the regression line to get values of predicted values of y. How do we find that line? We want to minimize our squared residuals. Residuals are just the difference between our actual values and our predicted values. So we're going to minimize the squared residuals, which is this equation right here. And don't worry, we're going to have the software or Excel do that for us. And when we go through that procedure, these are our formulas for the slope, covariance between x and y divided by the variance in x. And then the intercept is just equal to the mean of y minus our estimated coefficient, b1, our slope coefficient, times the mean of x. And that is how we will estimate a regression line. So let's do that. So I have our scatter plot again, and I had Excel create the true regression line for us. It's the red line, and we even have the equation for it, which is written right here. But what we want to do right now is actually find these things ourselves. So in Excel, I had it go ahead and calculate our covariance. So our covariance between horsepower and miles per gallon was negative 320, and the variance of horsepower was 4,700. So again, these were done in Excel. We're going to do this in our Excel lab this week. So let's go ahead and find our slope coefficient. So B1, the slope. So this is going to be the covariance between horsepower and miles per gallon over the covariance of horsepower. So if you prefer to think of it as just like x's and y's, so here I have x is horsepower and y is miles per gallon. So feel free to use that terminology, in which case it would be the covariance of x and y divided by the covariance in x. So this will be equal to, so we have these values right above us, 320.73 divided by 4,700.87. We get a value of negative 0.0682, which is what the computer gave us. If we look, our slope coefficient is right here. So does it make sense? Yeah, I think so. It's negative, and we obviously have this negative relationship. Recall our correlation was negative. And the magnitude is a little harder to tell, but the actual value is pretty small. And I think that's just because our x values are on a scale from 0 to 400, while y is only on a scale from 0 to 40. So that just means that x is going to move a lot faster than y, which is why we're getting a small value of 0.06. But let's go ahead and interpret this. So we would say for every unit increase in horsepower, gas mileage decreases by 0.0682 miles per gallon. So notice how I'm saying it, because we have a negative value. That means whenever we have an increase in horsepower, gas mileage decreases. Now, if we wanted to put this in units, that's a little easier to understand. We could just multiply both by 100. So what I mean by that is, so let's say equivalently, for every 100 unit increase in horsepower, gas mileage decreases by 6.82 miles per gallon. So all I've done is that instead of for every single unit, I'm now saying for every 100 unit. So all I did was multiply this value by 100. So when you multiply by 100, you just move the decimal place 2 spots. So 1, 2, that's how I get 6.82. But you don't have to do that. But this might make a little bit more sense. If horsepower increases by 100, gas mileage is going to decrease by about 6.8 miles per gallon. And that makes a little more intuitive sense rather than a single horsepower and 0.06 miles per gallon. That doesn't make quite as much sense. Okay, now let's go ahead and find our intercept. So again, I got this in Excel. So our average miles per gallon was 20.09, and our average horsepower was 146. So now we can calculate our estimate for the intercept, B0. So B0 is equal to Y bar minus X bar times B1 is equal to, so now we just plug these things in. So our Y bar here, our mean of miles per gallon, is 20.09 minus, so X bar is 146.69, and then we're going to multiply this by our slope, B1. And our slope we just found to be negative 0.0682. Right, that just came from right up here. And when we do that, we get a value of 30.099. So let's just check. Yes, that's the same value we got up here, 30.099. So if you were to think to just like extend this line all the way to up here, it's falling right about 30.099. So very close to 30. So that makes sense. And let's go ahead and interpret this. So the predicted gas mileage for a car with 0 horsepower is 30.099 miles per gallon. Now, this might not make a whole lot of sense. So the thing with intercepts is depending on the context of your data and your problem, it doesn't always make sense. So we might say this doesn't make a whole lot of intuitive sense. And that's simply because a car must have non-zero horsepower to move. But essentially what we're saying is if a car has no power, it could still move. It should get about 30 miles per gallon. And these cars, I think, are from like 1978. It's an old data set, so that might explain why you might think some of these gas mileages are pretty bad. Okay, let's do some prediction. So let's write out our estimated regression equation. So our estimated regression equation. So that is y I hat, our estimated value of y, is our intercept, so 30.099 minus 0.0682 horsepower, or what I'll do is write xi times xi. Or if I wanted to use words, I might say miles per gallon hat is equal to 30.099 minus 0.0682 times horsepower. So now let's do some prediction. So what is the predicted miles per gallon of a car with 200 horsepower? And then also, how about 250 horsepower? So let's do that. So let's do y hat would be equal to 30.099 minus 0.0682. And then, no, we're just plugging in for horsepower, right? So what horsepower are we interested in? Well, we're interested in 200 horsepower. So let's just plug that in. So times 200. And we get 16.45 miles per gallon. Now let's just do the same thing, but now let's plug in 250 instead of 200. So we would have y hat is equal to 30.099 minus 0.0682 times 250 is equal to 13.04 miles per gallon. So when we think about interpreting this, we're just saying, okay, we have this estimated regression line. So if we have a car with 200 horsepower, we would expect it to get about 16.45 miles per gallon. If we had a car with 250 horsepower, we would expect it to get about 13 miles per gallon. So it makes sense that this first car gets better gas mileage than the second because its horsepower is less than that of the second. 200 is less than 250, which is why we expect a higher miles per gallon compared to the second vehicle. And that's how we do prediction with our regression.